This video today is going to start our Chapter 9 Part 2. If you remember, we did Chapter 9 Part 1 before we started our E-line learning. In Chapter 9 Part 1, we did strictly solving quadratics. But now in this chapter, we're going to be graphing the quadratics. And just kind of to start out this unit, what we thought would be an easy way to kind of jump into this would be to talk about the three main parent functions that algebra we typically cover. So the first would be a linear function. The second would be a quadratic, which we're actually going to talk about how to graph in this unit. And then third, a cube function. And so what I'm going to do is just start off with classifying functions. We did this back in chapter 4 and talking about the features that a graph can have, components like being linear, nonlinear. If it is a function or not, there's a way that you can determine if your relationship is a function, if it is continuous or discrete, and then increasing or decreasing. So what I'm going to do is go through these three functions and talk about just kind of classifying the function first, and then I'll talk to you about how to start graphing a quadratic. So for the first picture here, as you see, you have a straight line. This is a linear function, and the equation would have y equals mx plus b format here. And if you wanted to find the equation of the line, you could. We don't need to do that here, but I know that this is a straight line, so I'm going to check that linear box. It's not nonlinear. It definitely is linear because I can take a ruler and put it up to that picture. Now, if you want to decide if a relationship is a function, this is how you do that. So any kind of graph can be a relationship, but what makes it a function would be if you have no repeating x values. And visually, what we talked about in class was taking like a ruler and putting it in a vertical way. And if your vertical line, your ruler, only crosses through your function one time only, then this would be called a function. But if your ruler passes through that graph more than once, it would not be considered a function. So relationships have points, x's and y's, but functions, you cannot repeat an x value and get out two different y's. So this would represent a function. Now these arrows mean that your function will keep going and going, which means it would be continuous and not discrete. Continuous means it continues on. Discrete means there's a beginning and an end point. And then as you look at your function from left to right, your function is going down. And so would it be an increasing or decreasing? Our line here is a decreasing picture because your slope here would be negative. You would go down to the right, down to the right, down to the right, which would make it decreasing. Now the next picture here, the parabola, I'm sorry, I forgot to finish this piece. So can you name what function this is? This is a linear function. And it would look something like this, y equals mx plus b. Now the second function here, the quadratic. A quadratic is a little bit different than a linear function. Well, first of all, it's not a straight line, so I'm gonna not check the linear box, I'm gonna check nonlinear, because this graph kind of looks like a U shape, it's curvy. And then as I'm looking at my picture, for me to decide if this relationship is truly a function, if I place my ruler down, will it hit that picture one time only? Yes, it will, which means it is a function. Now, continuous or discrete, these arrows imply that your function is going to go down and down and down. And so there really is no stopping point like discrete would have. So this would be continuous. And then for the next section, increasing or decreasing, how you determine if a graph is increasing or decreasing would be as you move from the left to the right. So this side of the graph, from left to right, it's going up. It hits this high point, and then as I continue to go to the right, it turns back down. So technically this graph is neither increasing or decreasing because it kind of has a component of both. So I'm not going to check these boxes because half of it increases. This part from left to right goes up, but then this part goes down. So this is going to be neither increasing or decreasing. This function here is a parabola, and this is what that function looks like. It's called a quadratic function. And it would look something like this, ax squared plus bx plus c. And you'd have to have a square component to your quadratic. Now the last picture at the bottom of your page, page 31 in the notebook, it looks like this. It kind of comes up, loops back down, and then ends going back up. This function is definitely not a straight line, so I'm going to check the nonlinear box because it has some curvy components. If I were to place a ruler through my picture anywhere, would it cross through only one time? Yes, it would, which means this would be a function. Would it be continuous? Would these keep going or would they stop? I'm going to check the continuous box because this pattern will continue to go up here and this side will continue to go down here. So that's continuous. And then for the last section, increasing or decreasing, you decide this from left to right across the picture. So from the left side of my picture, it goes up. It does dip down a little bit, but then the general flow, it continues to go up, up, up as we go from left to right. So I'm going to mark the increasing column for this graph. This type of function is called a cubic function. And this would have some type of cube. So I'm just going to write it as an x cubed. Go ahead and turn the page to the top of page 32, and then we're going to start graphing quadratics. Now I want to just kind of briefly talk about the quadratics that we're going to do first. If you notice here, I have y equals x squared compared to negative x squared, and I want to show you what the difference is between these two graphs. This is complemented by the next page in the notebook, page 33. So after I do my graph, I'm going to come over to page 33 and talk about the first graph question. So question 1, 2, 3, and then this extra question y. So first I'm going to do this graph and then I'm going to come over to page 33 and fill out the questions about that graph. So on page 32 of the notebook, it starts at the top with the equation y equals x squared. Now at the top of this picture, they give you this table here and they're telling you what x values to plug in. So we're going to plug in all of these x values, get our table, and then plot our points. So again, this is page 32. We're at the top. If I plug in the value -4 for x, it would look like this, -4 squared. Now make sure you use parentheses because I want to take my number -4 times -4, and -4 times -4 is positive 16. If I plug in the number -3, I want to take the number -3 times -3, which will end up being positive 9. Then I'm going to take -2 times -2 and get the number 4. Then -1 times -1, which is positive 1 when I square it. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. And 4 times 4 is 16. Now let's plot each of these points on this table. The grids go all the way out to like -20, so just kind of count carefully. So I'm going to go on my x-axis, my x goes left to right. I'm going to go over to -4 and then I'm going to go up 16. Okay, so here's my axis. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to find -3 and then go up 9. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go over 2 to the left and up 4. 1, 2, 3, 4. I'm going to go 1 left and up 1. 0, 0 is going to be another point on my graph. 1, 1, so right 1 up 1. Right 2 up 4. Right 3 up 9. And right 4 up 16. And if you notice, the picture is symmetric from the left side to the right side, which is kind of a cool feature of the quadratic. So if you get half of your parabola, you can kind of use the symmetry to help you fill out the other half of the graph. Now that I have this picture done, I'm going to go over to my notebook on page 33 and answer these questions. So what do you notice about this shape? What does the shape look like? Well, it's a U shape. They call this a parabola. The lowest point on this parabola, the point over here, this point, the lowest point, is the point 0, 0. There's a name for this. It's called the vertex. From that vertex, can you find the pattern to the placement of the points around the parabola? So for part A, when you moved left or right, how many did you go up? Well, when I went left 1, I went up 1. When I went left 2, I went up 4. When I went left 3, I went up 9. And when I went left 4, I went up 16. Do you notice how these values are squared? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. It also does the same thing when we go right. I know this said only left or right, but when we went right, the same pattern happened. Same pattern was used. When we moved left or right 3, we went up 9. Now what I'm going to do is go back over to this picture here for table 2, and I'm going to do the graph, but this time opposite of x squared. So how you're going to type this into your calculator is going to look like this. You're going to take opposite of the number in parentheses -4 and then square it. If you type that in exactly like you see that on the calculator, this is going to be opposite of -4 times -4, which is going to give you -16. 3 negatives end up giving you a negative. Opposite of -3 squared is going to be opposite of -3 times -3, or really opposite of what value we had before. So opposite of 9. Opposite of -2 squared, opposite of -2 times -2 is going to be -4. Opposite of -1 squared, so opposite of -1 times -1. -1 times -1 is +1. Now times that opposite sign out front would make this -1. Opposite of 0 squared, well, I'm not going to get a positive or negative with 0. 0 is kind of the tiebreaker between the numbers. Now opposite of 1 squared is opposite of 1 times 1, which is -1. Opposite of 2 squared is -4. Opposite of 3 squared and opposite of 4 squared is -16. Now what I'm going to do is make a picture on my graph using these points. I'm going to go over 4 to the left and down 16. I'm going to go over 3 down 9. Over 2 down 4. Left 1 down 1. 0, 0. Right 1 down 1. Right 2 down 4. Right 3 down 9. And right 4 down 16. If I connect these points with the parabola U shape, this is what it would look like. Now what I'm going to do with this picture is jump over here to page 33 and answer the questions here, and then I'm going to come back and answer that why do you think this is happening. For graph number 2, this upside down parabola, number 1 says what is the difference? What is the difference about this graph from the first one? Well, this time our graph is upside down because of that opposite sign. It faces the opposite direction. Number 2, what about the pattern for plotting the points? Is this pattern a different pattern from before? Well, the pattern that we talked about over here was our squares. And so -4 times -4, right? We got -16, but this time it said opposite, so we went down 16. And again, 3 times 3, you see that 9 show up. 2 times 2 with 4, 1 times 1, 1. And that's where it represents that square function, which is the same as what we had before, but this time the only difference is that instead of going up, we went down. So the same pattern, but this time we just went down, not up. So right 1, down 1, right or left, actually 2, we went down that number squared. Right or left 3, we went down 9. And right or left 4, we went down 16, which should kind of make sense because we squared our values. Now, why do you think this is? Well, if you have the graph y is equal to x squared, we're squaring our input to get our output. All right, now I'm going to jump over to page 34 on your notebook. Now we're going to do 2 more graphs, but this time I'm going to use x squared plus 2, and then I'm going to use in parentheses x plus 2. And I want you to see that there's a very big difference between these 2 types of functions. Here you have your x term alone, x squared, and then a constant of 2. And now you have a group. So the x and the 2 are going to be added together before you square that sum. So notice there is quite a big difference between these 2. So now I'm going to start with the same kind of process. I'm going to start plugging in numbers, and then once I get my input and my output, I'm going to graph over here. The first number I'm going to plug in is -4. So what I'm going to do is take -4 times -4, and then I'm going to add 2 to that number. -4 times -4 from the other page, if you look back at table 1, we got 16. 16 plus 2 is 18. -3 squared plus 2 is going to be 9 plus 2, which is 11. -2 times -2 is 4, positive 4, and 4 plus 2 is going to be 6. -1 times -1 is positive 1, plus 2 is going to be 3. 0 times 0 is 0, and if I add 2 to it, I get 2. And now the same process, but with positives. 1 times 1 is 1, plus 2 is 3. 2 times 2 is 4, plus 2 is 6. 3 times 3 is 9, plus 2 is 11. Sorry, my dog is barking in the background. And then 4 squared is 16. 16 plus 2 is 18. And now what I'm going to do is graph these inputs and outputs. So I'm going to go left 4 and up to 18. Left 4 and up all the way to 18. Left 3 up 11. Left 2 up 6. Left 1 up 3. 0 up 2. Over right 1 up 3. Right 2 up 6. Right 3 up 11. And then right 4 up 18. So this is very similar to the original shape that we had, but do you notice what's different about it? If you go back and compare from the original graph, so let's just take a quick peek. What's different about this graph? Where did it go? Do you notice how this graph to this graph, it went up 2 units? That's what we're going to talk about on page 35. So graph 3 that we just did, this is page 35. There are a few questions about this. What happened to the vertex on this graph? It moved up 2 units. Why do I think it moved? Well, we added 2. What do you think would happen if 3 was added to it, or if 5 was subtracted? Well, if we added 3, we would have moved up 3 instead. But if 5 was subtracted, instead of moving up, what do you think would happen if we were to subtract? We would have moved down 5. Number 4, did the pattern for plotting the points change from this graph? If you notice and compare these 2 pictures, I mean, if you could really put them side by side, they look an awful lot alike. Do you notice how the pattern really didn't change at all? Instead of being at 0, we just went up to 2. And instead of being at 1, we were up 3. Instead of being 4, we were up 6. Instead of 9, at 11. So we were using the same pattern, just up 2 units. So I'm going to talk about that pattern change over here. No, the pattern did not change. Still, your pattern would be whether you move left or right. If you go right 1, you're going to go up 1 from the vertex. So I'm going to write that down, from vertex. If you go from the vertex right or left 2, you're going to go up 4. If you go 3 units right or left from the vertex, you went up 9. And the same thing with 4, you're going to go up 16. Now I'm going to go back to page 34 and finish this graph in the parentheses x plus 2 quantity squared. So in parentheses, I'm going to take -6 plus 2 and then square it. This is going to make -4 squared, which is going to be -4 times -4, or 16. -5 plus 2 is going to make -3. And if I take -3 times -3, I'm going to get +9. -4 plus 2, and if I square it, I'm going to have -2 squared, and -2 times -2 is +4. -3 plus 2, if I square this, it's going to be -1 squared, which is 1. And then -2 plus 2, if I square this, is going to be 0 squared. -1 plus 2, if I square this, it's going to be +1 squared, which is 1. 0 plus 2 squared, this is going to be 2 squared, which is 4. 1 plus 2 squared is going to be 3 squared, which is 9. And 2, my input is 2, plus my 2 squared is 4, and I'm going to square that. Now I'm going to plot each of these points. I'm going to go left 6, up 16. Left 5, up 9. Left 4, up 4. Left 3, up 1. Left 2, 0. Left 1, up 1 from the origin. 0, 4. 1, 9. And 2, 16. If you notice this graph from the original that we had over here, so just kind of to compare it, our original had a vertex at 0, 0, and look where your vertex moved this time. Where did it go? Did it go where you expected it to go? I think what's unique about this one is I would have assumed, well, if this one went up, this one probably isn't going to do the same thing because it looks a little bit different. But I think I was surprised that this one actually moved left. It's opposite of the direction that I anticipated, because when I think +2, I think over here on the right side. But if you notice, we took these numbers, and when we added them, we really did go left too. So I think that's kind of unique about this one over here. So now I'm going to go over to page 35, and I'm going to answer the graph 4 questions over here. Where is the vertex on this graph? This graph, our vertex moved to -2, 0. So it moved left, which surprised me. I thought it would have moved to the right, but it didn't. Why do I think it moved? Well, our function was x plus 2 squared, so I would have guessed right. But no, it went to the left. For number 3, it says, notice that 2 was added to the x and then squared, but our vertex is -2, 0. What do you think would happen if 2 was subtracted? So what if we had had this instead? So if this graph moved left, what would be opposite of that? If we use a subtract sign, opposite. Well, if we use opposite, oops, I can't spell, opposite of right, I'm sorry, opposite of left. Did we just say we moved left? Then we should move 2 to the right with this function. Sorry that I messed that up there, you guys, but we did move left, so opposite of that would be moving right. Number 4, did the pattern for plotting the points change with this graph? From our vertex? No. If you look at the vertex, if we went right 1, we went up 1. Out 2, we went up 4. Out 3, we went up 9. Out 4, we went up 16. So from the vertex, our pattern did not change. And number 5, knowing what you know now know, where do you think the vertex would be for this equation here? So knowing that this function moved left, and knowing that this function moved up, if we combine these two together, this would mean your function would move left 2, and this means your function would move up 2. Now I'm going to go to page 36 in the notebook, and now I'm going to show you what happens when we have in the front a multiplier. So we showed up, down, left, right, and now I'm going to show what happens when you have a number out front and how that might change our picture. So for these two graphs, if you want to pause it and plug in the numbers or speed ahead after the graphs are done, feel free to do so, but I'm going to do them all by hand. So for the kids who really just want that extra little bit, please feel free to keep going right along with me. If we use our Pemdas, make sure that you follow your order of operations correctly here. An exponent comes before we multiply, so make sure that we do our exponent of 2 before we multiply by 2. So I'm going to take -3 and square it before I multiply by my 2. -3 squared is 9, and 2 times 9 is 18. I'm going to take -2 squared first, and then I'm going to double that. Then I'm going to take -1 squared first, and then double it. I'm going to take 0 squared first, and then double that. Then I'll take 1 squared. 1 squared is 1, then double it, I get 2. 2 squared is 4, and if I take 2 times 4, I get 8. And then if I take 3 squared, I get 9. 9 times 2 is 18. Now if I plot these points, notice how the graph changes just a little bit. I'm going to go from 0, 0, I'm going to go left 3, but this time up to 18. At -2, I'm going to go up 8. At -1, up 2. 0, 0. Right 1, up 2. Right 2, up 8. And right 3, up to 18. If I connect my parabola with some points, notice how this is a little bit different than the picture that we had originally. So this was our original x squared, and this is now double x squared. Notice how when we go out 1, we didn't go up 1. When we went out 2, we did not go up 4. And when we went out 3, we did not go up 9. We went up more than that. We actually went double the normal rate. So as I look over to my last page here for the notes for today, page 37 in the notebook, I'm going to answer the questions about this table over here. So this is again page 37. How did this parabola's appearance change from all of the other problems that we had so far? Well, this is a little bit skinnier. I said that this graph rose faster. So instead, when we went right or left, 1, we went up 1 times 2. When we went right or left 2, we normally went up 4, but this time we went double that. So I said it was going faster than before because we went up more than before. For number 2, what happened to the pattern for plotting the points? How many did you go up when you went to the left or right? I said double the normal amount. Letter B, how about when you went left or right 2. Well, before we went up right or left 2, we went up 4, but this time we went 2 times that 4, so 8 up. Letter C, how about when you went 3? Well, normally when we went right 3 from the vertex, we would go up that number squared, which would be 9. But this time, we went double that 9, which was the 18 movement, up instead. Why do you think that is? Well, we took the number 2 times our x squared, which means we would go up double the normal x squared rate. We have one more graph. Our notes are almost done. Hang in there. You're doing an awesome job. And if my dog keeps barking at the neighbor, just think of it as something fun. For table 6, this is our last graph. We have a half x squared. Think about what happened here, that our graph went up double the rate. What do you think you might anticipate here with half of x squared, half times x squared? So again, make sure that you follow Pemdas, which means your exponent needs to come before you multiply. So I'm going to take a half of -6 squared. So half of 36, which is 18. Half of -4 squared, make sure you do the square before you multiply. Half of 16 is 8. Half of -2 squared would be half of 4, which is 2. Half of 0 squared, well, 0 times anything is 0. Half of 2 squared, so half of 4 is 2. Half of 4 squared, or half of 16, is going to be 8. And then half of 6 squared, half of 36 is 18. Now what I'm going to do is plot those points on my grid over here, and I'm going to finish up by answering graph 6 questions. So as I'm looking at my grid, I'm going to go left 6 and then up 18. Now left 4, up 8. Left 2, up 2. 0, 0. Right 2, up 2. Right 4, up 8. And all the way to 6. We normally didn't go out that wide, but out to 6, and then up to 18. Compared to our original graph, this graph is definitely wider, and I know we didn't track all the numbers. See here, we didn't go to -5, -3, -1. We skipped some of those, but I do notice that this graph is definitely wider than the one that we had before. So our original y equals x squared graph, that's what I've been comparing to. So now what I'm going to do is go over here to my last thing for the day, graph 6. I'm going to answer these questions, and then we're done for the videos. Thanks for paying attention this long. Great job. Number 1 says, how did this parabola's appearance change from all the others? I said that this one was wider, or maybe you want to call it like fatter. For number 2, what happened for the plotting of the points? How many did you go up when you went left or right 2? Well, when we went left 2, we went up 2. And if you don't remember, just look over here. Left 2 or right 2, we went up 2. How about when we went left or right 4? Well, when we went to 4, we went up 8. And when we went over 6, we went up 18. Why do you think that is? Well, we took half of that number that we inputted squared. So we took half the normal square rate. Great job paying attention today. Please make sure you fill out your homework assignment on your Canvas page. Make sure you do the instructions that your teacher told you, and I look forward to doing the next lesson with you. Stay safe, stay well. I hope the best for you.